Okay, y'all, we are back with another part of the lesson of 1.3. So, for the first two lessons in 1.3, we were looking at slope-intercept form and point-slope form of a line. And in this last lesson, now we're going to look at how can I use equations of lines in general to help model data in the real world. And we're going to start by recognizing that if we're trying to interpret data from the real world, we're probably going to go ahead and graph it on a scatter plot. We're going to look at what are the variables that I'm comparing and how do they correlate with each other. And when I do that, what I'm trying to do is to determine a regression or a relationship between those two variables out in the real world. And when I'm describing that correlation, I can look and see, does that data trend upward? And does it have positive correlation? Does that data trend downward and have negative correlation? Or is that data kind of spread out and random and it just doesn't look like there's any pattern to it? And I always have students who say, well, you can just draw a line right through the middle. And sure, I could draw a number of different lines, but that doesn't really help me predict what's going to happen in the next, if I extended either of the axes, like what's going to happen with the next data that I collect in the future. So we would call this having no correlation. And it's important for us to recognize right now that both of these have what look to be like a mostly linear relationship. It looks like it goes up or down in a line. Data doesn't have to be linear, but since we're focusing on lines in chapter 1, that's just what we're going to look at with our data for now. And then as we move through other chapters, we'll look at more interesting regressions as we go on. Okay, so if I do have some sort of pattern, if it does have positive or negative correlation, we can go ahead and create a regression equation. We're going to do this very first example by hand, but for our other examples, we're going to do it with technology because realistically, that's probably how you're going to model data in the real world is with technology. So the first thing we need to do is we've collected data about the temperature at different depths in a lake. And we need to identify which of these is my independent variable and which one is dependent on the other one. And so temperature is going to depend on how deep we are taking the measurement in the lake. It's not the other way around. So since temperature is dependent, that means that depth is independent. And so I'm going to put depth on my x-axis and temperature on my y-axis. And that is always the order that you want to graph those in, is always independent goes on the x-axis, dependent goes on the y-axis. Okay, and my data for my x's look like I need to get up to 15, so maybe I'll count by 2's here. So I'll go ahead and label that 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and that's good enough because I only have to get up to 15. Okay, and my temperature, we always want to start at 0, so I don't want to do a jump on my y-axis here, but I do need to get up to 85. So let's see if counting by 5s, 5, 10, 20, 30, 40, 50, 60. So counting by 5s isn't going to be enough, so maybe let's go ahead and count by 10s then. So we will go ahead and do 10, 20, 30, 40, 50, 60. Oh, that was silly. 70, 80, 90, 100. Okay. And let's go ahead. It's not going to be perfect, but that's okay. Let's go ahead and just do the best we can to plot these data points. So 0, 85 is probably about, let me use a bigger dot. 0, 85 is about, oh my goodness. There we go, about right here. 482, so 482, 781, 1079, 1277, and 1576. Okay, so just by oh my goodness, I don't know why all those dots are such different size. Okay, this definitely doesn't form a perfect line, but I can definitely tell it's going down a little bit, and it looks pretty linear, so I'm just gonna do the best I can to draw a line that goes down. Mostly goes through those points. Maybe I could have used a straight edge to draw that a little better. Okay, and in order to do this by hand, we just need to pick any 2 points to write a line of best fit, okay? This isn't going to be perfect, especially because we might end up with different equations if we choose different points, since the data doesn't perfectly line up. But I'm going to go ahead and just choose the first point and the last point. Let's choose these two and write a line of best fit that goes through those. So I'm going to go ahead and write those ordered pairs. We have 085 and 1576. Okay, so let's go ahead and write the slope. And let's see, that's going to be 9 over negative 15. Don't forget that negative. I can simplify that a little bit, so negative 3/5. And I am going to choose y-intercept form because I can very clearly see that that y-intercept is 85 there. So y equals negative 3/5 x plus 85. So that is going to be my best guess at a line that goes through that data. Okay, and then I can go ahead and predict the temperature of the lake at 25 feet. So that's going to be the depth is 25. So I'm going to go ahead and plug in the 25 for, oh, and you know what? I used x and y in this equation, but my data was in terms of d and t. So maybe I should go back and let's rewrite this where t is my dependent variable and d is my independent variable. There we go. So that makes it a little more natural to plug these values in. And I can go ahead and predict the temperature by plugging in 25. That is going to be negative 15 plus 85, so 70 degrees Fahrenheit is my prediction if I were to take the temperature down at 25 degrees. I'm sorry, at 25 feet. Okay, but you might have had a different prediction if you used 2 different points to write your line. So then the question is, how do we make sure that we're getting the same answer? And we can do that with our graphing calculator. So you're definitely going to have to pull your graphing calculator out. I'm so sorry I don't have the program on my iPad to show you to work alongside me, but I have the steps written out right here. So on your graphing calculator, you want to find the button that says stat. I'm going to zoom in over here, and that is going to be this button right here. So we can see that stat button. And if you click that, you want to press enter because we want to edit the data in our stat plot. And we're always going to enter our x values into that first list. And the fast way to do it is to type a number and then just press enter. and it'll automatically put that number in the list and let you start typing the next one. And then scroll over and you're going to enter all of your Y values into that L2 list. You need to make sure to type them in order. So like for this first example in example 2, we're going to type all of the time is always my independent variable. So all of these values are going to go into my L1 list in order. And then all of these values are going to go into L2. And once you have all of that data put in, I like to press second quit to go back to the regular calculator screen. Okay, and then you're going to press stat again. But this time you're going to scroll over to the menu that says calc. And then option number 4 is that linear regression, and it's going to give it to you in slope-intercept form, which is super nice. Okay, so for this first example, second example now, you research the average cost of whole milk for several years to look for trends. The table shows your data. Okay, and I mentioned that we are just going to list all of these in your L1. That's not really the best thing to do. I'm going to show you a different strategy on the back that comes up with a nicer looking equation that tends to work a little bit better. But for now, just starting out, there is nothing wrong with you just typing 1,998 for the year. Again, not best, but I'll teach you something else in a different example. So let's go and enter all of those into L1. Enter the cost per gallon into L2. Once you have that, press second quit. And then we're on step 2 now. So you're going to, that's supposed to be a little star. You're going to press stat again, move over to calc, choose linear regression, just press enter, 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 enter through that list. And it is going to come up and tell you what the regression equation is. So, pardon my dog. Okay, so that regression equation should tell you, and I'm going to write 2 things here. So it's going to tell you that y equals, and then it has a value for the slope down below. So that slope is 0.09343x. And then it's going to have a value for your y-intercept, minus 184.05076. Oh my goodness, all dogs. Okay, my directions in this problem say to round to the nearest thousandth. Well, an interesting thing happens is if we round, we end up getting a different answer for part B. So let's look at what happens. So I'm going to go and follow directions and round to the nearest thousandth. Okay, so there's my answer that it asked for. Beautiful. Okay, but in part B, ask me how much would you expect to pay for a gallon of whole milk in 2022? Okay, well, 2022 is the year, so I typed that in for my x's. And we left this as numbers in the thousands. Okay, so I'm going to plug 2022 into both of these equations, and I want us to compare what happens. Okay, so if I plug 2022 into that top equation, I get which doesn't really make sense for a number answer, so let's go ahead and change that to $4.86. Okay, but what happens if I had used that bottom equation? So if I do 0.093 times 2022, then I subtract 184, 0.051. We end up getting that the cost of milk is only $3.99, which actually, if I were to round that correctly, it ends up as exactly $4. And that is a huge difference in my estimated price of milk. That's almost a whole dollar different. So this is a great example of why you should never round in further calculations. So we do want to round on part A because the directions tell me to. But then whenever I want to use an answer to calculate something else, I don't want to use an answer that I've rounded things in, because this is going to be the better approximation than the one where I had rounded answers and then I'm rounding again, because the more you round, the more error you are introducing into your estimation. So realistically on the test, I would accept either of these because the directions in part A did tell you to round. But I need you to know that in the real world, when you are doing this for a job in the future, which I know that sounds ridiculous, but it's actually fairly likely, because this is a great application of algebra, that you never want to use rounded values in further calculations. Okay, so let's practice some more with our graphing calculator. Practice entering data and coming up with that regression equation. Okay, so use a graphing calculator to answer the following questions. The table shows the number of people P and suitcases S on 8 different airplanes. Okay, so P is going to be my L1 list, S is going to be my L2 list. Go ahead and go in your calculator and enter this data in. Once you've entered that data in, press second quit. Click stat again, scroll over. Option number 4 is to create that linear regression, and you should end up with, I'm going to write the unrounded one first. You should end up with the equation. Remember, we're using S instead of Y, so I'm going to do S equals P instead of X. Okay, and then I'm going to go ahead and follow directions, and I'm going to round to the nearest tenth. So S equals 1.8P minus 16.5. Okay, but then for my predicting, I want to use the unrounded equation. Predict the number of suitcases on a plane with 500 people. So P is 500. So I'm going to go ahead and use this equation, and I'm going to plug in 500 for P. And you should end up with which, let's think of this answer. This is a word problem. I'm predicting the number of suitcases, and it doesn't really make sense for suitcases to be a decimal, so I am going to go ahead and round this, that my prediction is really a little bit closer to 901 suitcases. And keep in mind, you might have ended up with a slightly different answer if you used this equation, which is okay. I just need you to know that that is not best. And speaking of best, I told you there was another way to do example 2. And instead of just typing in the years into L1, we want to use smaller numbers. It just makes our regression equation a little bit easier to interpret, understand, and even just to write down. So I'm going to go ahead and instead of using thousands for all of my years, I'm going to let my X value be the number of years since that very first year that's listed. So years since 1985. Well, 1985 is 0 years away from 1985, so that one gets a 0. 1991 is 6 years after that, so I'm going to use 6. 1993 is 8 years after 1985. You get the idea. So this top row, those are the numbers that I'm going to actually enter into L1. So this is going to be my L1 list. This is going to be L2. And we can go ahead and type those in the calculator. Go ahead and pause because I already have mine all filled out and pulled up here. But I have that y equals, I'm going to write the unrounded one first. Then I'm going to go ahead and follow directions and round to the nearest hundredth. And I just get much smaller numbers since I'm not using numbers in the thousands for my input there. Okay, and then for predicting the salary, I'm going to go ahead and use the unrounded equation. 2020 means that I am 35 years away from 1985. So I'm going to plug in 35 into that top equation, and I get 41.5 million dollars, right? And I just went back and read the problem to figure that out. The table below shows the salary in millions made by the highest paid Major League Baseball players. All right, and then a super common SAT and ACT problem. So Jayla plotted data from her science project as a scatter plot. She found the line containing 2 of the points to be this one. So it kind of seems like she did go through 2 of the points, right? I can see she went through this point right here and this point right here. And so she created the equation of a line. But I hope that we can see with our eyeballs that that's not a great prediction of the line. We should have used 2 points that make the line look more like this. Would be a much better line of best fit. Okay, so to transform her line into a more decent linear regression, what must she do? Okay, so she needs to increase both the slope and the y-intercept. Okay, well, increasing the slope of hers is definitely going to make it more steep. So I think increasing the slope is good. But the y-intercept needs to go down. We need to decrease the y-intercept. So I'm going to say A is not a good reason, or I'm sorry, A is not a good answer for that reason. Increase the slope. Yes, we want the line to be steeper. And decrease the y-intercept. Yes, I wanted the y-intercept to go down. So I'm looking like B is probably my best bet. Decrease the slope. No, we don't want her slope to decrease. Decrease the slope again. Leave the slope unchanged. No, we definitely need it to be more steep. So B is definitely my best answer. And that is linear regression. I believe that is our last lesson before we have our first half of this chapter test. So happy studying.